For many materials, resistance rises with temperature. Hotter material, higher resistance. Colder material, lower resistance. One of the interesting side effects of this is if you run a current through something, it will heat up. Power equals voltage times current. So the component will heat up and its resistance will go up the longer it's used. We can show that by tracing voltage versus current for this little lamp here, which functions as a resistor. Here's our lamp, and here's our curve tracer. This device will increase the voltage across the lamp and measure the current. The vertical axis is current, the horizontal axis is voltage. Towards the tail end, we can see the lamp start to light up. So we see early on, as the voltage increases, the current increases linearly. Then it starts to heat up, at which point the current drops because the resistance has grown. The interesting transitive effect is that it looks like it has a negative resistance for a short while. But that's just because the resistance is still changing at that point. By this section, it is already heated up, and you can see it has a much higher resistance, i.e. a much lower slope, than it did at the beginning. Now we can directly show the correlation between resistance and temperature by taking this length of copper wire and then just directly changing its temperature. We're going to send a current of about 200 milliamps through it and measure the voltage across it. The higher the voltage, the higher its resistance. Then we're going to change its temperature and see if that voltage, and therefore resistance, changes. We'll start by blasting it with a heat gun. We can see blasting it with some high temperature air isn't enough to drastically change its properties, but we did increase its resistance by about 10%. Now we'll try the opposite. We'll dunk it in some liquid nitrogen and see what happens when we cool it. It doesn't take long to get it cold enough that it's already lost more than 30% of its resistance. Of course, no matter how cold we get this copper, we're never going to get it down to zero resistance. Now in general, when you lower the temperature of a conductor, its resistance goes down and its conductivity goes up. But they're both still finite. There are some materials, though, that at low enough temperatures have zero resistance and infinite conductivity. They're called superconductors. Their properties require that they're not made out of pure metals. For example, I have here this yttrium barium copper oxide, or YbCO. It's a relatively high temperature superconductor, in that its resistance goes to zero at about 92 Kelvin, or minus 181 Celsius. So we'll show that here by mapping its resistance versus its temperature. Liquid nitrogen has a boiling point of 77 Kelvin, so we should be able to cross that 92 Kelvin threshold. We can see the temperature and resistance both falling together. Then around 100 Kelvin, it starts to fall precipitously. And below 90, it stays pretty close to 0. In this particular run, it looks like it sticks at around 96.5 Kelvin.